Hey there, math fans. I'm going to talk about how we interpret partial derivatives, in particular, second partial derivatives, because students often ask me about this. And then we'll finish with the discussion of Clairaut's theorem, which is about the mixed partials. And I'll give you a little bit of history. But briefly, I have these two surfaces. One kind of looks like a Pringles chip, this one. And I'm standing at some point here. I think it's actually 1, 1. So here we're at in both these pictures. Turned it a couple different ways, and I'll talk about that in a second. But imagine you're standing at the point 1, 1. And this is also 1, 1. And I think for this one, I use the point 2, 2. So this is 2, 2. I mean, that's the xy value. And this is 2, 2. And I'd like to say a couple things about it. Now, you can plug into the function to get the height, meaning f of 1, 1 would tell you the height. So let's go all the way back here. The height is 0. So that's what that means. It means it actually at 1, 1 is on the xy plane. This one, g of 2, 2. Oh, and I forgot I changed my function slightly, so let me make a slight adjustment. This is plus y cubed. So you'd compute whatever this is. 8 minus, I didn't intend to do this. This is probably a mistake. I'm writing this out. 8 plus 8. 8's cancel, negative 10. So that right there is at negative 10. Apologies if that calculation is wrong. As I said, I didn't intend. But let's just leave it. You can tell me I'm wrong in the comments. Okay, so that's the height. Now let's say we want the slope. Now, what we mean by slope is slope in the positive x direction. So the two directions we walk are the positive x or the positive y in these pictures. And that means you got to be careful when you're looking at it. You're standing here, but you're looking in the positive x direction. When you take a step, is that going to be uphill or downhill? That's what we call the slope in the x direction. This other picture you're seeing over here is looking this way. So we're standing here at this point, and we're looking in the positive y direction. So you should see, or I hope you can see, that this slope is positive. You're going up, and this slope is negative. So I would call that downhill in the y direction. And this would be uphill in the x direction. That's what we mean. So when you compute the first partial, that's asking the rate at which your height is changing with respect to x. This is going to be the derivative if y is kept fixed. This is the derivative if x is kept fixed. If you plug in 1, 1, for instance, then you get f of x of 1, 1 is equal to 2, and you get f of y of 1, 1 is equal to negative 2. And that tells me the slopes. So this is the slope in the x direction. It's uphill with a slope of 2. And this is also a slope. In the y direction, it's downward, it's negative 2. That's what those numbers mean. So let's do the same thing for this one. Most students get that eventually. So with respect to x, this is going to be 2xy minus y squared. Those two terms don't have an x in it. With respect to y, they all have a y in it. Minus 2xy plus 3y squared. And you could compute the derivative with respect to x at 2, 2. I said I didn't intend to do this, but this is not bad. 8 minus 4, it's going to be 4. It's uphill. Good, because that matches what I'm seeing. It does. It's a little hard to see because the x direction is this way. And I feel like I've turned it. Maybe I've turned it inappropriately because this one looks like the x direction. This one looks like the y direction. So I don't know why I flipped it, but here's the x direction. I'm getting that the slope of that line is 4. If I was standing here, it's uphill at 4. So I flipped these two from where I had intended. Maybe that was on purpose. I don't know. Anyways, you put a 2 here, you get 4 minus 9. So let's do the partial with respect to y. At 2, 2, it's going to be 4 minus 9 minus 8 plus 12. Negative 17. It's negative 1. Yep, negative 1. So that's looking this way. If I'm standing here and I look in the positive y direction, it's going to be slightly downhill. Those were a little harder to see just because of how I turned that. That was unintentional. But that's what those mean. Those are just slopes. And it always means looking in the positive x direction or positive y direction. Okay, so what about these second partials? Well, the second partial with respect to x says take the derivative with respect to x in, and you get 2. That's concavity. We've actually seen that before. So if you just do x twice, you're still considering the same curve. And so in class, I'm going to be saying things like, is that concave up or concave down? It's concave up. We can see that. It's concave up in the x direction. Similarly, you can see right here that this one's concave down. So it's concave down in the y direction. Right now, I'm just talking about the particular point I'm talking about. This one looks like at the point I'm looking at, it's concave up. So it looks like right there, it's concave up. And that's in the y direction because I flipped my pictures. We're looking in the y direction. And this one looks like it's also concave up. So concave up in the x direction. Okay, so let's compute that second partial. So we got a 2, that sort of matches. Let's do down here, I'll do the y twice, the y and y. It's negative 2, concave down. So that matches, concave up, positive, concave down, negative. And I'll show you some visuals of this in a second, but that's what it means. If you are looking in the x direction and you increase x, your slope goes up. If you're looking in the y direction, you increase y, your slope goes down. Okay. And similarly, you can do g twice. I'm leaving something off, but we're going to come back to it. This is 2y. And you can do y twice here. And that's going to be negative 2x plus 6y. And at 2, 2, you get that this is positive. So it's concave up in the y direction if I plug in a 2 there. At 2, 2, you get negative 4 plus 12. So it's positive 8. It's concave up in the y direction. Those are positive. Okay, what I've left off is what we call the mixed partial. So if you take the derivative of this with respect to y, you actually get 0 because there's no y there. If you take the derivative of this with respect to x, you get 0. That's called the mixed partial. And it says, how does the slope change if I increase the other variable? Meaning if I step to the side. Students who play video games tell me this is called strafing. I'm going to step to the side slightly, and then I'm going to look at the slope in the x direction again, and I'm going to compare these two slopes. If it goes up, it'll be positive. If it goes down, it'll be negative. Okay, this one's more interesting because if you do the mixed partial with respect to x again, with respect to y after you've done x, you're going to get 2x minus 2y. If you do the derivative of this one with respect to y, you're going to get 0, 0, negative 2x. Something looks off to me. Ah, yes. Did I miscopy something? 2xy minus y squared. Okay. And then with respect to y was x squared. Oh, I'm doing with respect to x. So this with respect to x is 2x, good, minus 2y. They're the same. This is Clairaut's theorem, that those are always the same. In this case, let's see if we can plug in our number 2, 2. Oh, it's 0. So at that moment, it seems that that's 0. So usually the biggest question students have is, what does this mixed partial tell us? Everything else should be familiar. It's concavity in the x direction, concavity in the y direction, concavity in the x direction, concavity in the y direction. So what about this mixed partial? And I'm going to show some visuals, and then I'll finish with some history. So here's the Pringles chip. Here we're at the point 1, 1, and I'm currently looking in the y direction. So the question is, if you're looking in the y direction, let's go to the point 1, 1. And I'll show all of these things just briefly. So you're looking in the y direction. You have a slope at a particular point, and you increase y. If I increase y, what happens? The slope goes down. I'm concave down. So if I go back to a negative number, now I'm going to increase y, slope goes down. That's what that -2 means. So what I just visualized was this. How does the slope change in the y direction? If you increase y, well, it goes down. It's part of a frown. Okay, how does the slope change in the y direction if you increase x? Let's increase x. Ooh, it doesn't change. If you change x, it doesn't change. So what I just illustrated there was this number. If you're looking in the y direction and you increase x, it does not change your slope. That's the mixed partial. So then the other things measure the other direction. Here we go. You're looking in the x direction. What happens if we increase x? Slope goes up. If you increase x, slope goes up. It's concave up. That's what this is. What happens if you're looking in the x direction? Let's go to the point, and you increase y. Stays the same. That's the mixed partial. These things measure the same thing, so they're the same. There are certain conditions, like if things aren't continuous or the derivatives aren't continuous, you can have unusual behavior at certain points. But generally for functions whose derivatives are continuous, these are always the same. Okay, what about the other one? So let's look at the other one. Here's that point 2, 2 I was talking about. Currently it's the slope in the x direction. So let's look at that. The slope in the x direction is positive. We did it. It's 4. Now let's see what happens if we increase x. It increases. That's what this is. And at 2, 2, this would be 4. It would be positive. It's concave up. Now it's going to depend now on different values depending on where you are. But anyways, let's go back to 2, 2. Now if we increase y, what happens? Let's watch that line. So if we increase y, ooh, it stays the same. At least for an instant. That's what we were seeing in the mixed partial. Now if I go somewhere else, I don't know, here, and I increase y, you can actually see the slope goes down. So it's going to depend on where you are. Okay, similarly, if I go look in the other direction, slope in the y direction is negative. It's that -1 we saw. If you increase y, it's going to be concave up. But now you can see it actually depends. If you go further back here, if this was your value of y, then it's actually concave down, and there's like an inflection point, and it's concave up. So it always depends, because in this case, the formulas have variables in them. Whether it's concave up or concave down is going to depend on where you are. It's nice that we have the formulas to tell us. Okay. So then lastly, the mixed partials. Again, if I'm standing here, currently I'm looking in the y direction, and it's a positive slope. So let's increase the x and see what happens. Increasing the x, increasing x. Looks like it stayed about the same there, but then started to get steeper. So these ultimately give us a measure of what's happening. And the interesting thing will be like when we get to the bottom here, get to this peak value, we can use the things that we're seeing to tell us stuff about concavity there. In fact, at that low point, it's concave up in all directions, which means it's some sort of minimum. The mixed partial ensures that something weird is not happening in another direction. So we'll talk about that. We won't do a formal proof, but it helps us check if we have a so-called saddle point, because it is possible to have a point where the slope is 0 in both directions and have it concave down one way and concave up another way. And sometimes it's hard to find that, but there's a way to get it. So here's like a point that's kind of like that. That's a saddle point. And it's concave down one way and concave up another way. It turns out the mixed partials help us see that, and it comes up as part of a formula. Okay, so there's the visuals. I'll end with a little bit of history. So, previously I talked about history of Clairaut. It published this work. So here's what I found, a little bit of Wikipedia research. So it was after Newton. Clairaut was somebody who followed Newton and tried to prove some of the questions he'd asked. But in 1740, he published an article that included this. Now, I found the article. It's in French. I couldn't see something that wrote Clairaut's theorem in the way that we write it now. It's written in a little different form. But an interesting thing was, so it's named after him because he was the first to kind of mention it in an article formally. Then others studied it. His proposed proof, it was sort of, so what proof meant was, what are the conditions? And the conditions now, there's a lot of ways people can say it, but you need continuous second partials. The reason it was hard is I think it was probably hard to find counterexamples, meaning examples that didn't have continuous second partials, but also it didn't work. It often didn't work at a particular value. When you search for counterexamples, they're kind of obscure. And I noticed that everyone gives the same couple counterexamples. And I'm not an expert in this area. So for all intents and purposes, for what we consider, second partials are equal, and they can be used as a way to check your work. Like it's a way to check your first partials. If your second partials aren't equal, then that probably means you messed up your first partial. So it's a nice way to check like that. But I guess there was a long history of trying to formally prove this over a long time. So anyways, and then later this Schwarz actually gave sort of the most rigorous proof. So it's sometimes called Schwarz's theorem or Clairaut's theorem. Clairaut because he's the first to formally write about it in this way. Schwarz because he actually proved it. Anyways, so that's kind of an interesting history. Hope that gives you a little bit more background. Ultimately, you should understand that has something to do with measuring the concavity around a point. And that makes sense because it's telling you how the slopes are changing around that point. All right, thanks for listening.